Alrighty, folks, so getting started here now on the next lesson of Chapter 2, we're going to be looking at relative motion. Again, just a reminder, make sure you are following along with the notes, okay? If you're able to print them out, great. If you're just following along on loose leaf, that also works, okay? But we want to make sure we're actively engaging. Our brains will just get so much more out of it that way. All right, here we go. Let's dive into Lesson 2. So most of what we've covered so far in Physics 20 has dealt with objects that move through a medium just being, whatever it's moving through, like maybe that's the medium as they're walking along the road or they're swimming through the water, whatever it might be. The medium is the road or the water there, what they're moving through or on, okay? So far, we've looked at things where that medium, whatever they're moving in, is stationary relative to our frame of reference. Now that's some fancy terminology, but all it really means is that so far, if we've been thinking about, measuring the velocity of this car as it drives along the road, right? We didn't have to think about, if we're standing here measuring its velocity, how fast it's moving, we're not thinking about whether or not the road is also moving, right? Because that would change how fast overall it was moving relative to us standing over here, right? So for example, when a person went for a walk, we did not have to worry about how fast is the ground moving, because relative to us, the ground isn't moving. Same situation here, right? If we were asked, how fast is this car moving compared to us? Well, we can just figure out how fast the car is moving because we know that the road itself is stationary relative to us, right? You can probably guess based on that setup that today we're going to look at situations where sometimes the medium through which the object moves is also moving relative to us. So that could be a situation like this, for example, right? So now we have a river that is already moving relative to us as we stand here outside the river, right? But then within that moving river, there's a boat that's now moving at its own velocity, right? So not only is the boat moving, but the river that it's moving through is also moving. So if we wanted to figure out the velocity of this boat overall relative to us, we're going to have to factor in the fact that the river itself is moving, right? Unlike this situation, where if we wanted to calculate the car's velocity away from us, right, we just have to think about how fast the car is moving because we know that the road itself is not moving relative to us. And that's kind of the whole idea behind what we're doing today. So it's going to be a lot of what we've been doing. It's just adding vectors. It's just that in the previous lesson, a lot of the vectors we were adding together were displacements. Now we're just going to be looking a little bit more at adding velocities, right? Adding, for example, the boat's velocity and the river's velocity in a situation like that. So in these cases where we have something moving, but what it's moving through is also moving relative to us, we need to consider how the motion of that medium is going to affect the overall motion of the object as viewed by someone who is stationary relative to both the object and the medium, right? So if this guy here is measuring the velocity of the boat, he has to think about not only how fast is the boat trying to move, but also how fast is the river moving as the boat moves through it, because he is stationary relative to both the river and the boat. Okay, so just a quick note on some terminology here. You're going to see these terms thrown around, okay? Things like still water velocity, still air velocity, they can swim or fly at, all of those, they all refer to the same thing. It's just the speed at which an object or person can move regardless of the direction they're facing or regardless of what's going on around them. It's essentially saying how would they move if the medium they were in wasn't moving. Right? It's the velocity they will be aiming with. We're going to see that come up today. So coming back to this example here, right? The boat does have a velocity that it's capable of moving at, right? In still water, right? It's just that it's not moving through still water, so we're going to have to add that velocity to however fast the water's velocity is to get the overall movement relative to us, okay? So the velocity of the medium will add to this still water velocity or still air velocity, and that will give us the resultant velocity as viewed by someone who is stationary, standing off to the side. So we're going to start out simple and just think about a boat moving in a river here. Okay, I'm going to hop over an animation so we can visualize some stuff here. So I'm just going to start out by making it so that this river is actually not moving, okay? So you can see the velocity of the river up here. I'm just going to make it 0. So this is just still water, okay? And down here, I'll make it so that the boat is moving to the right at, doesn't really matter, 2.5 meters per second. So here we go. Well, that's what happens. The boat moves at its velocity to the right? The water isn't moving, okay? So that's not that different than what we were dealing with before with, say, a car on a road. But let's now change things up where the boat is moving, but so is the river, okay? And you can see here, there's a little vector addition diagram being drawn, right? There's the velocity of the boat, how fast it could move through the water. It's still water speed. But then we have to add on to that how fast the river itself is moving, because the boat is moving through that water, but the water itself is now moving at 3 meters per second to the right. So if I run that, you'll see it appears to be going faster relative to us who are standing on the ground, right? Because now not only are we watching the water flow, but the boat is moving through that moving water at its own speed. Okay, now I'm going to try one more thing here. I'm going to aim the boat. Now nothing's changed about the boat. It still has its same, engine and everything. So its speed is still the same. Its velocity is 2.5 meters per second, but now to the left. The river's still flowing to the right, so now watch how that looks, right? Our boat actually appears to be going, well, not only is it going slower, it's actually going backwards from the way it's trying to go, right? Notice the velocity of the river is moving 3 meters per second to the right. Our boat is only moving through that water at 2.5 meters per second to the left. So overall, to us, it actually appears like it's slowly going to the right? The river's velocity is kind of winning here, so to speak. I can even adjust the boat's velocity. Let's just actually match the river's velocity and see what we think happens. So now river's flowing 3 meters per second to the right. Boat is moving through that river 3 meters per second to the left. What do you think that's going to look like for us standing on the ground watching? Well, let's see. Right? It actually appears to us as if the boat is standing still, right? It is moving through the water at 3 meters per second to the left, but the whole water itself is moving to the right at 3 meters per second, right? And so for us standing on the ground watching, it looks like the boat isn't moving at all. If I make the boat a little faster, right, it starts to now beat out the river. Okay, but because it is moving through the water, while the water itself moves in that other direction, those velocities overall to us, who are standing still relative to both the river and the boat, we see the combined velocities in action. So if a boat is moving against the current of a river, right, it's going to appear to be moving slower than its still water speed to someone who's standing on the shore, because the river's velocity is working against the boat's velocity. Again, it's not like the boat's engine changed and it's any slower, but if we're standing off to the side of the river, right, it's going to look like the boat is moving slower because it's moving through that water at its still water speed, while the water itself moves away from us at a different speed or towards us, depending on how it's set up. Okay, so for example, if a boat has a still water speed of 10 meters per second and moves upstream means against the current, against a 3 meter per second current, an observer on the shore is going to see the boat moving at, 10 meters per second. This is in the opposite direction, so opposite directions need opposite signs when we add vectors, right? They're going to see it as moving at 7 meters per second, okay? And we've defined here the negative direction as the direction of the current. So this is going to be upstream. It's against the current, right? We got a positive answer. And this really just comes down to vector addition, right? If we have a boat moving 10 meters per second that way against the water current, which is 3 meters per second in the opposite direction, right? Well, then our resultant velocity, how the boat will actually look like it's moving relative to us on the ground, is going to be a little bit smaller than that 10 meters per second. In fact, to put it precisely, 3 meters per second less, as that current works against the boat's velocity. Now, if the boat is moving with the current in the same direction, it's going to appear to be moving faster than its still water speed because it's moving at that still water speed through the water, but the water itself is also moving in that direction. So if we're standing off to the side on the shore, right, it's going to look like it's going as fast as it can go plus the water's velocity on top of that, right? In that case, the river's velocity works with the boat's velocity. So for example, if a boat has a still water speed of 10 meters per second and it moves downstream, so now in the same direction as the current with a 3 meter per second current, well, now those are in the same direction. So same sign, positive 10 meters per second for the boat plus positive 3 meters per second for the current will show us that for us standing on that shore, that boat overall is going to be moving away from us at 13 meters per second or towards us, depending on where we're standing. Okay, so 13 meters per second, downstream now. Okay. And so again, tip to tail, right? The boat is capable of moving with that velocity, but the water it's moving through is at that velocity. So our vector addition diagram shows us that we should get a resultant velocity for us standing on the shore that's even larger, right? The sum of those two vectors. Okay, let's try out an example here, a very similar example. A plane can fly with a speed of 400 kilometers per hour. So we want to know what is the actual or the resultant speed that we would see looking at that plane from the ground, right? If there is a tailwind of 50 kilometers per hour. Okay, so terminology, tailwind, what does that mean? Well, it blows on your tail, right? So meaning if you have a plane, right, we think of its head as being up here, its tail as being back here. So a tailwind blows like this. Do you think that's going to make the plane faster or slower for someone watching on the ground? It'll make them faster, right? It helps them. It's pushing them from behind, okay? So drawing a quick diagram here, as we always should, okay? We've got our wind blowing like that, and we're told that it is a tailwind of 50 kilometers per hour. And the plane itself can fly at a speed of 400 kilometers per hour. So that's how fast it can move, regardless of, like if it's in still air, that's how fast it's capable of flying. That doesn't change when there's wind. All that changes is the wind adds to that velocity, right, for someone standing on the ground watching. So this plane is going along, flying through the air at 400 kilometers per hour. It's just that the air itself is also moving at 50 kilometers per hour. So if we draw a vector addition diagram here, we've got the velocity of our wind and the velocity of our plane tip to tail. They're in the same direction. So we can predict that our resultant velocity should be, well, faster, right? Faster than 400. Now, these are all in one axis. They're just in the x-axis. That won't always be the case today, but for now they are, right? So we can just add them up algebraically. We just have to be very careful to make sure we give opposite directions, opposite signs. I'm going to go ahead and call the direction the plane and the wind are going positive, okay? So now we can just say our resultant velocity is going to be the result of adding those two things up, right? And so we know that our plane is moving at 400 kilometers per hour. But while it's doing that, the air it's in is moving at 50 kilometers per hour. That's the wind. And so we get that the resultant velocity of the plane, as viewed by someone on the ground, is going to be 450 kilometers per hour, right? If we're sitting here, we're going to say that plane is moving overhead at 450 kilometers per hour because it's moving through the air at 400 kilometers per hour, but then the air itself is also moving at 50 kilometers per hour relative to us. Okay, now, what if there's a headwind? You can probably guess a headwind blows on your head, so it's against you. Okay, so if we draw our quick diagram here, we've now got a wind that's working against us. Okay, so that wind is blowing 50 kilometers per hour, but it's in the opposite direction that our plane is flying, which is still capable of moving at 400 kilometers per hour, but now the air that it's moving through is actually moving in the opposite direction of the way it's trying to go. Okay, so let's draw a quick VAD, as we always should. So now the plane's velocity tip to tail with the wind's velocity, and we can see that the resultant velocity for someone observing this from the ground is going to be a bit slower than 400, right? You might be able to do in your head right now how much slower, okay? But again, that's because if we're watching from the ground, yeah, the plane is flying at 400 kilometers per hour through the air, but the air itself is going 50 kilometers per hour in the opposite direction it's trying to go. So that's going to impact the overall velocity as viewed. But same idea, they're both in the same axis here, so we're safe to just add them up as long as we remember to give opposite directions, opposite signs. So that means I need to be really careful here, right? I'm going to choose to call the plane's velocity positive here, but I need to then make the wind velocity negative because it is going in the opposite direction as where our plane is trying to go, right? So 400 plus negative 50, we find that the resultant velocity is just going to be 350 kilometers per hour in whatever direction the plane was trying to fly, right? So as we watched this plane go overhead, standing on the ground, we'd be saying, okay, so relative to us, it's only moving at 350 kilometers per hour, right? It's still flying through the air at 400. It's just that the air itself that it's moving through is going in the opposite direction at 50. So overall, to us, the plane appears to be moving at 350 kilometers per hour. Towards us or away from us, depends where we're standing. Okay, so those are some one-dimensional examples, right? So fairly straightforward. We add them up because they're just in the same axis, okay? And we are going to continue to just add them up in 2D, but we know that dealing with vectors in 2 dimensions requires things like, separating into their x and y components, adding up, all those skills you learned in the previous lesson, okay? Just now applying them to velocities.
Okay, so when we look at this relative motion, these relative velocities in 2 dimensions, usually what's going on here is we have, a situation, something like this, where a boat is now trying to move in one axis, right? It's trying to go across the river maybe, but the river itself is moving in a different axis. Okay, so the river is maybe flowing from left to right, and the boat is ultimately trying to get over here. So we've got the river's velocity in what we would call the x-axis, and the boat's motion is going to involve some y-axis stuff, okay? Now, that's why there's 2 dimensions, right? We've got x and y, so we're going to deal with it the same way we dealt with in the previous lesson. We have to keep the x and the y separate, right? Can add x's to x's, can add y's to y's, but we can't mix them. And all that Pythagorean theorem and trigonometry stuff will come back. So just to kind of give you an overview, there's basically 4 different ways these can be asked, or 4 different scenarios that we might see, okay? And really, there's like 2 and then different types of those 2, okay? So the big 2 categories are compensation and off course, right? So we either have a situation where an object does not compensate for the motion of the river, and as a result, it gets blown off course, right? It doesn't end up where it was trying to go, okay? Or the object could compensate for the motion of the medium, and as a result, it manages to overcome the fact that the water is moving. It corrects for the motion of the water and gets to its intended target. Okay, we'll look at those in a bit more detail here. This is just a general overview. And then we can have off-course and compensation problems as well. You'll notice the difference here, single variable versus multiple variable. Like the name suggests, all that means is that if it's a single variable problem, you're only going to need to think about one type of vector to solve the problem. It's usually either velocity or displacement. More often than not, it's just velocity. Okay, with a multiple variable problem, it's just got an extra step thrown in there where you'll need to think about 2 types of vectors. It'll pretty much always be the velocity and the displacement, as well as time to fully solve the problem, right? So usually that just involves, okay, you figure out the velocity and then you use time to figure out the displacement, or vice versa, something like that. Okay, so all the same physics concepts, just an extra step of connecting velocity to displacement through time or something like that. Let's take a look at each scenario in a little more depth. So in general, a compensation scenario simply involves the object's velocity canceling out the velocity of the medium with a component of its own velocity, right? So for example, if we have a boat that's trying to go straight across this river, right? If it's trying to go straight across this river. Well, if it just aims itself straight across, it's not going to make it straight across, right? Because as it's aiming itself this way, the river's velocity is also going to be carrying it to the right at whatever velocity the river flows with, right? So that's not going to compensate for the motion of the river. If we think about, okay, well, the river has some velocity horizontally, right, in our x-axis. So to compensate for that, our boat needs to cancel out this x velocity, and it can do that by introducing an x velocity of its own, right? By giving its own velocity an x component that's just as big but in the opposite direction of the water's velocity. So if this is how the boat aims itself, it's going to point, off to an angle, then if we break that down into its x and y components, right, if that's the velocity of the boat in the x-axis, and then of course it also has a y component, okay, but this x component will cancel perfectly with that x component, so that overall the boat's velocity, as we measure it from the ground, is not going to have an x component, right? This plus this, they'll cancel out, and then the boat's resultant velocity will only be in the y-axis, right? That's the idea here. We have an x velocity we need to cancel out, so aim the boat so that its x component cancels out the water's velocity, which is all in the x-axis. Drawn as a vector addition diagram, we can see the ideas at work here, right? We have the water's velocity to the right, tip to tail, we need to add the boat's velocity so that it cancels out with the water's velocity, right? So if our boat aims itself like that, then when I go to draw the resultant velocity, how the boat actually moves as measured by someone on the ground, we'll see that it just goes straight across, right? The boat is aiming itself like this so that its x component perfectly cancels out the water's velocity. For contrast, if the boat had tried to just aim straight across, right, well, look what its resultant velocity would be. Because that water's velocity still gets added in there, right, well, now our boat actually moves off at some velocity at an angle because it's being carried by the water in the x-axis. So that's what we're going to see down here when we look at off-course problems. So if we look at this visually, right, you can see right now I've got the river moving to the right at 3 meters per second, and the boat aiming straight across right now, okay? So look at that vector addition diagram that it draws for us. The boat's velocity is straight across, but we need to add in the river's velocity, and so the resultant velocity, well, it goes off at an angle, and so it doesn't actually get where it wanted to be. That would be an off-course situation. If the boat wanted to compensate for that river's current, right, well, look at the situation. Which way would it need to kind of aim itself to cancel that out? The river flows to the right, so you got it. It needs to introduce some horizontal component to the left, right? And so if it aims slightly to the left now, right, now we see it actually does move, and it overall ends up going straight across. And if you look at our VAD there, you can see that's what we would predict. By aiming itself slightly to the left, its x component cancels out with the river's horizontal velocity so that it ends up going straight across overall. All right, so we just talked about it quite a bit when looking at compensation, but let's officially look at the off-course scenario, okay? So what this is going to involve is the object's velocity being aimed straight across, right? So they don't try to compensate for the current. They point their boat, for example, just straight across the river, right? And so as a result, what's going to happen? Well, the boat is going to move across the river in the y-axis, but at the same time, they're going to be moving in the x-axis at however fast the river is carrying them, right? So they move in the axis of the medium's velocity at the medium's velocity, right? So the boat aims straight across the river, but at the same time, it's being carried by the river, in this case, to the right, right? And so it's not going to end up here by the time it gets across. It's going to be somewhere off course. And it's, again, just a result of the fact that velocities are vectors. So these multiple velocities, they add like any other vector would, right? Tip to tail. There's the velocity of the water. There's how the boat is trying to move through the water, right? And so as a result, overall, the boat's actually going to end up
moving like this for this person here standing there, right? They're going to see the boat end up somewhere over there. Okay, so the basic method here is a lot of the same stuff you're used to, right? I mean, that's the general problem-solving process. Things like writing out your givens, okay? I know I mention it a lot, okay? But it is so important here. Like, you'd be amazed at how much of solving these problems just comes down to drawing your VAD, right? If you draw your vector addition diagram carefully, thinking carefully about whether it's a compensation or an off-course problem, okay, you are seriously like more than halfway there, right? Once you draw the diagram, it usually is just a quick matter of some Pythagorean theorem and trigonometry to figure out what you're trying to find, okay? So draw that VAD and then solve for the missing vector. It might be the resultant or it might be one of its components, okay? It might be the hypotenuse, it might not be the hypotenuse, but that really so much of this boils down to drawing the correct vector addition diagram and finding the unknown vector, okay? Pythagorean and SOHCAHTOA are going to get you where you need to go. Okay, so let's go ahead and try out some examples. We'll start with the single variable examples and then we'll look at some where we have to, connect displacement to velocity through time or something like that. So, example 1. So a boat has a still water speed of 10 meters per second, okay? So remember, still water speed, that means that's just how fast the boat can move through the water, right? If the water's also moving, we'll have to add the water's velocity to it in order to figure out its, resultant overall velocity, but that's how fast the boat can move through the water. So that's V boat. That's the velocity it's going to be aiming with. There is a 5 meter per second current from the west. So that's the velocity of our water. We want to figure out the resultant velocity of the boat, okay, relative to the ground. So someone standing on the side watching, if the boat steers through the river heading north. So heading north, they're heading north, right? What does that mean? Well, that means they're aiming straight across, right? So let's draw a diagram here to start to get our bearings. We've got a boat, and we know that its velocity, it's capable of moving with 10 meters per second, but it's heading north, right? So is this an off-course or a compensation problem? This is going to be an off-course problem, right? Because the boat is aiming straight across, but it's forgetting that the river is carrying it, to the east in this case, because it's from the west, right? If the current is coming from the west, that means it's to the east. So what's going to happen when we draw our VAD, we're going to see here that, well, if I take the boat's velocity, right, and then tip to tail, I add the water's velocity, right? The resultant velocity, remember, resultant vector, always from where we started our diagram to where we finished our diagram. The resultant velocity looks like that, right? So overall, the boat is going to be moving like this, okay? Yes, it's got its own motion across the river, but at the same time, the water's carrying it to the east. So we know that this is 5 meters per second, right? And we know that the boat's velocity is 10 meters per second. So I'll just add those to our diagram, and we are looking for that resultant velocity, right? So see what I mean? Just drawing our VAD here, how could we solve for this side of the triangle when we know that this is 10 and this is 5? Well, this is a right angle triangle. It's aimed north. This is to the east, so that's a 90-degree angle, right? We just need to find the hypotenuse of this triangle and we'll have found its resultant velocity. So we can just use here, when we have two sides, we can use the Pythagorean theorem, right? So the resultant velocity squared will equal the velocity of the boat squared plus the velocity of the water squared, okay? And I'm already ready to just square root both sides, plug in my values, and solved. So let's go ahead and do that. So it'll be the square root of 10 meters per second squared plus 5 meters per second squared. So that means we're going to have the square root of 100 plus 25, or 125 meters squared per second squared. And taking the square root of that, I got 11.1803 meters per second. So that is how fast our boat is going to be moving overall, right? Makes sense that it's a little bit faster than 10 because now we're also adding on this horizontal component, right? Again, it's not 10 10 plus 5, because those are in different axes. We know we can't add y's to x's that simply, but using trigonometry, we can figure out what that combined velocity would give us. Okay, now that's the speed, that's the magnitude, how fast it's going, but it's a velocity, it's a vector. We need to get the direction as well. Okay, so once again, look how handy our diagrams come in, right? Our VAD here, we can now see, okay, if I wanted to communicate that direction, one way I could do it is by finding that angle and then correctly referencing that angle to north and east, right? Using that to describe. So I've drawn it this way, so I'll probably go ahead and, set up my triangle this way and find the angle that way, right? We technically have all three sides, but again, there was one more calculation involved in finding this one, so it's usually a bit safer to just use the values the question gave you because you know they're right? So looking at this, I know that opposite is 5, and I know that adjacent is 10. So thinking of SOHCAHTOA, right? I have opposite and adjacent. We can use tan here to find that angle. So to describe that angle, opposite, again, would be 5. Adjacent would be 10 meters per second. But we don't want to find tan of theta. We want to find theta itself. So we need to take the inverse side of both sides. Sorry, the inverse tan of both sides. And doing that with, second tan on my calculator, I get that theta is 27 degrees. Okay. So we're almost there, right? We've got how fast they were moving, and now we know what that angle is. But be careful. Common student mistake here would just be to say 11.1803 at 27 degrees, right? But don't forget, if we just say 27 degrees, right, what that's going to imply, this is 0, this is 90, and we rotate counterclockwise by our angle, right? So if we just said 27 degrees, that would say that this angle here is 27. So always, make sure you're confirming with your VAD that that's actually what you're trying to say. And in this case, it's not, right? We don't want 27 degrees from the x-axis. We want 27 degrees from the y-axis here, right? From north, not from east, okay? So we need to be a little more specific here. We could say 27 degrees. And in this case, right, if we say, okay, we've got north, we've got east, we know that this angle is 27 degrees. So what we could say, right, should we say 27 degrees north of east or 27 degrees east of north? Right, from north, we are 27 degrees east of it, right? East of north, not north of east. So putting it all together, to two significant digits, our boat's overall velocity will be 11 meters per second at 27 degrees east of north. And there we go. And just a side note before moving on here, because sometimes students will ask, well, what if I had drawn my vector addition diagram this way, right? It's totally okay, right? We went over this in the previous lesson as well, but just a reminder, okay? Again, you might have drawn it this way, and your angle would be this angle, and what you would do is when you did the inverse tan of now opposite is 10, adjacent is 5, you would find that that angle was 63 degrees. And that's totally okay. You're just going to say, instead of saying 27 degrees east of north, you're going to say 63 degrees north of east. So that would be a totally acceptable answer to this question as well. Okay, 27 degrees east of north is the same as 63 degrees north of east. Those are the same direction, just one uses start east and go 63 degrees towards the north. One says start north and go 27 degrees towards east. You end up facing the same direction. Okay, you could have even just said just 63 degrees, because in that case, that really is what we mean, starting from 0 and going counterclockwise 63 degrees. Okay, let's try out another example here. So a boat attempts to cross a river. The dock lies 25 meters directly north. Okay, let's start drawing our diagram right away. Sometimes it's helpful to just add information to the diagram as soon as you get it. So we now know that the distance across the river, right, it's 25 meters directly north. I'm going to call that dy because it's entirely in the y-axis, directly north. But the river ends up pushing the boat at a resultant angle of 10 degrees east of north. So again, first things first, let's figure out what that actually looks like. So very careful here, east of north. So that's saying starting from north, go 10 degrees towards the east, right? So that you're east of north. Okay, so that means our boat actually ended up doing something like that. This is 10 degrees. So if we think about what our boat actually did, right, it ended up going, somewhere. I'm going to draw the angle a bit exaggerated here maybe, but it really did that. Okay, so it was 25 meters straight across to the dock, but our boat didn't go straight across to the dock. It ended up moving at an angle 10 degrees east of north. And so what we want to figure out is the distance downstream that the boat will land. So what that means is, how far is it downstream from where it was trying to go, right? It was trying to go here, but it ended up, well, I should maybe draw the dock there then, I guess. It was trying to go to the dock, right? How far did it end up downstream of the dock? Well, if we take a look at that, we can see, okay, really just what I need to find then is the boat's horizontal displacement, right? It ended up with a horizontal displacement because of the river pushing it, okay? So let's just draw out our diagram here. It did go 25 meters to the north because it did cross the river. It's just that at the same time, it went east, right? It went east while it was going 25 meters north, okay? Overall, it did something like this. It moved off at an angle, okay? And we know that this angle here is 10 degrees. It got pushed 10 degrees east of north. So taking a look at this, look, we want to know the side that's opposite. We have the side that's adjacent, and we have the angle. So if we think about that, right, we have adjacent, we want to know opposite, and we have the angle. We can set up a tan ratio equation here that will help us solve, right? The tan of 10 degrees is going to equal the opposite side, which is the side we want to find, divided by the adjacent side, which we already know is 25 meters. So look at this, right? We have everything in this equation except for one unknown. That means it's solvable. So to solve for dx, we need to isolate it. Right now, it's being divided by 25 meters. So to undo that, I can multiply both sides by 25 meters, giving us that dx, its horizontal displacement, is going to be 25 meters times the tan of 10 degrees. And this is just regular tan, not second tan, right? We're taking the tan of 10 degrees. That's just a number you can put in your calculator and multiply it by 25 meters to get that their horizontal displacement is going to be 4.40817 meters. Okay, so that is how far they're going to end up downstream from the dock. So to two significant digits, because that's what we were given in the question, we'll say 4.4 meters, and we can even reason that that will be to the east, right? Because if the river pushed them east of north and they were headed north, well then their x component of their displacement was to the east. So in Smarter Marks or on a Scantron sheet, we would start in the left box. We would say 4.4. Okay, the decimal does get a box, and it's okay that we don't need all four boxes. We just leave the last one blank. All right, see what I mean though? 90% of that was just drawing our diagram correctly. From there, it's just some grade 10 math. Let's try example 3. So a squirrel is being chased by a dog through the forest. The trail he can use to escape is directly south across a river. Okay, let's already get going and just start adding some info to our diagram. So the trail is directly to the south of where our squirrel is. All right. Now, the squirrel majored in physics at Squirrel College. Smart squirrel estimates that the river is flowing at 0.5 meters per second west. Okay, so there's the velocity of our water, right? And it's in the x-axis. So I'm going to go ahead and draw that in. The velocity of the water. Now, if the squirrel can swim at 1.5 meters per second in still water, what direction must he swim so that he reaches the trail, right? So is this a compensation situation or an off-course situation? Right, we want the squirrel to compensate. We want him to adjust for the fact that the river is pushing him to the west by introducing an x component to the east to his velocity. So we do not want the squirrel to aim that velocity straight across, because then these will add and he'll end up going west of where he wants to be and might get caught by that dog, right? So how do we compensate for this? Which way does he need to aim? Right, he needs to aim slightly to the east to cancel out that westward component, right? That's going to be how the squirrel aims their velocity. And now again, the whole reason for doing that is so that now the x component of the squirrel's velocity, how fast they're moving horizontally, will cancel out the water's velocity, which is also in the x-axis. So that overall, what the squirrel ends up doing is going straight across, right? When we draw our VAD, we can see that a little more clearly here. So if I take the squirrel's velocity off at some angle and add the water's velocity tip to tail, right? We're trying to get it so that overall what the squirrel really does, its actual velocity, the resultant velocity, is straight across the river, right? So that if we were standing here on the trail, what we would see is the squirrel move at some velocity straight across. They are aiming slightly, well, they're aiming at an angle into the stream, right? But then the stream's velocity cancels out that component, and so overall they have no x component and just move straight across. Now, what we're trying to figure out here is what direction must he swim. So we actually could find the resultant velocity. We have this and we have this. We could use Pythagorean theorem to find it, but we actually don't need the velocity itself. We just need the direction, right? So we just need to figure out what is that angle and where is it relative to northeast, southwest. So looking at what we have, we want this angle, we have the side opposite to it, and we have the hypotenuse. Okay, be careful there. Common student mistake is to assume VR is the hypotenuse, because often the resultant is our hypotenuse, right? But not in this case. Our VAD shows us that actually no, it's the squirrel's velocity that's the hypotenuse of this triangle. So we have opposite and hypotenuse. What does that make you think of? Sine, right? SOHCAHTOA. So we could say that the sine of theta is equal to the side opposite. So that's our 0.50 meters per second over hypotenuse, which is our 1.5 meters per second. Opposite over hypotenuse. Okay, now we didn't want to solve for the sine of the angle. We wanted the angle itself. So to get rid of that sine, we need to take the inverse sine of both sides. And doing that gave me that theta was 19.47 degrees. Okay, and so now all that's left to do, we just wanted the direction, right? So we just need to be careful about our 19 degrees, right? Remember, again, if we just say 19, people will think we mean this, right? Which is definitely not the direction we want to say, right? That's totally wrong. We want somewhere between south and east, not somewhere between north and east. So all we need to do is think about, okay, based on our diagram here, right? How does this relate to north, east, south, and west? Okay, well, the diagram shows us, right? This would be straight south, and our angle is between there, right? So this is 19 degrees, okay? So all we need to say is, from south, go 19 degrees towards the east. So we are 19 degrees east of south. 19 degrees to the east of south. And there we go. That's our answer. And same quick side note here, right? Again, you might have drawn your VAD like this and therefore approached the angle slightly differently. That's okay. If you found that as being the angle, you still have a correct answer. You're just going to say, instead of saying 19 degrees east of south, you would say 71 degrees south of east. So that's also a valid answer for which direction the squirrel should aim to get straight across. 71 degrees south of east is the same thing as 19 degrees east of south. Okay. Let's try another one here before it's your turn. So a boat has a still water speed of 18 meters per second. That is how fast the boat is capable of moving through the water. The captain must take the boat north, so must take the boat north across a river that has a current of 4.5 meters per second to the west. Okay, with what heading. So heading is a fancy word for direction, right? With where do they need to aim should the captain steer her boat, right? So essentially we can tell that this is a compensation scenario, right? They want to compensate for this current so that they end up going straight across the river overall. Okay, so let's draw our diagram. Okay, so the water is flowing to the west. I'm going to make this multiple choice. Which way roughly should the captain aim in order to get straight across? Is it option 1, 2, or 3 that I've drawn there? Pause the video, take a second, think about it, and then once you've got your answer, justify why that's the direction that makes sense. Okay, ready? I'm going to reveal the answer. It is option 3, right? And in your justification, you hopefully referred to the fact that, well, we need to cancel out this horizontal velocity, right? And so what we need to do is introduce another horizontal velocity from the boat by aiming its velocity to the east, right? This is to the west. We need to cancel it out with a component of the boat's velocity that's to the east. We can't change how fast the boat goes, but we can change where it's aiming, and therefore what the x and y components of the boat's velocity actually are. Okay, so let's draw our VAD. We've got the water flowing to the west, and then we're going to add our boat's velocity to that, and we're trying to do it so that, notice here, the x-ness of this boat's velocity perfectly cancels with the x-ness of the water's velocity, making our actual resultant velocity look something like this, which is what we wanted, right? We wanted it straight across. And again, we know the boat's velocity, it's 18 meters per second. We know the water's velocity, it's 4.5 meters per second. If we wanted to find this actual velocity, we could with the Pythagorean theorem, right? We would say 4.5 squared plus VR squared has to equal 18 squared because that's our hypotenuse, right? And then solve for VR. But in this case, we actually don't even want to find that velocity. We just want to find the direction. Which way does she need to aim, right? So that's going to be an angle here. And the way I've drawn my VAD, it makes the most sense to find that angle. Again, reminder, not this angle. Sometimes students will find that angle, but that's at the end of the vector, right? We're trying to say, where do you aim? You can't aim from like the end. You have to aim from where you are now, okay? So we're finding that angle theta. What do we have? We have adjacent and we have hypotenuse. So TOA, right? Adjacent over hypotenuse will be the cosine of our angle. So let's write out that ratio. The cosine of our mystery angle will equal the adjacent side divided by the hypotenuse. Okay, we don't want cos theta, we want theta. So take the inverse cos of both sides. And I get that theta is 75.52 degrees. Now we're not quite done. We need to place this between northeast, southwest, right? In this case, the way I've drawn it, we are here, right? This is 76 degrees. So that would be 76 degrees north of east. Okay, so she should aim 76 degrees north of east. Of course, if you had set up your VAD a little bit differently, you probably would have found this angle, right? And you would have gotten the correct answer of 14 degrees east of north, okay? So that's okay, that's still what we're describing. 14 degrees east of north is the same direction as 76 degrees north of east. All right, so go ahead and pause the video and try this one out right now. And if you're looking for, right at this time, a little more practice, you don't want to wait until after the video to, do all of your practice at once. These are also some good ones to try out at this point in time. Okay, I will make note that these ones here, they're a little more complex, but they're all skills you have. Okay, they just involve a velocity, multiple velocities where you have to think about their x and y components. Okay, but it's still the same process, still the same thoughts driving all the thinking and the problem solving. You just might first need to separate some stuff into x and y components. Okay, or as always, you can wait till the end and do all of your practice, but at the very least, you need to pause right now and do this one here. Okay, and then we're actually pretty much done. We just need to now look at those multiple variable examples, which is similar stuff. We're just going to now have to think about a displacement and a velocity and potentially connecting them through time. So as we've been talking about, right, when an object moves through a moving medium, both its resultant velocity, the result of adding its velocity to the medium's velocity, as well as its resultant displacement, so where it actually ends up, are both affected by that medium's motion, right? We also know how to relate those displacements and those velocities by considering the time that has passed. And it's even easier because this is actually uniform motion, right? So we can just use good old V equals d over t, right? We can relate velocity and displacement through time, because velocity is simply the rate at which displacement is changing. So how much did displacement change per second? Now this is true for the resultant velocity vector as well as for all of its components. And that is the key thing to keep in mind here. Okay, the biggest student mistake with these is mixing up the velocity and the axis that it's in with a displacement that's actually has nothing to do with that velocity because it's in a different axis, right? So the rate at which our vertical displacement changes, how far we went, let's say across the river, the rate at which that changes is how fast we were moving across the river only, right? The rate at which we move horizontally is the velocity we were moving horizontally only. And the rate at which our overall displacement, how we actually moved, changes is our actual resultant velocity. So we don't want to mix those up, right? We can use dry with vry, but we can't use dry with vrx because that's its horizontal velocity and it has nothing to do with how far it would move vertically. Let's try to visualize this a bit. So I'm going to start out with this river not moving. So this is just a still piece of water, okay? And I've got the boat going straight across the river here, right? So I want you to think about, right, how long will it take to cross the river? Well, we can think about the distance it has to go vertically, which is across the river, right? And the velocity at which it's moving vertically. And we could do a v equals d over t to figure out. You can see there, it looks like it took it about 10 seconds to get straight across, right? So the distance it had to go to get across the river was vertical. So it's just the vertical part of its velocity that decides how long it takes to get across. Now, if I make the river move, has anything changed vertically? No, right? Our boat still has the same velocity and it still has to go the same distance across the river. So if we just think vertical here in the y-axis, notice it still takes about 10 seconds to get across. The time looks slightly different. I think that's just a little, quirk in how it's calculating in the simulation, right? But that makes a ton of sense because yes, it is moving horizontally, right? But it's moving vertically with the same velocity, and it still has to go the same vertical distance. In the y-axis, nothing has changed. It's just that while it's doing that in the y-axis, it's also moving in the x-axis. So between this situation, where it goes straight across, and this situation, where it aims straight across, but at the same time it's being carried sideways, nothing has changed in terms of the time it took to go across the river because that's a y-axis displacement. And so it's just the y-axis velocity that determines how long that's going to take, right? All that changes when we add in the x velocity is that, okay, while it went across the river, it was also going downstream. And so that emphasizes, hopefully, the importance of keeping your y's with your y's, your x's with your x's, and your, at an angles with your at an angles at the same angle, right? The horizontal velocity has nothing to do with the vertical distance it's going to travel. It only determines how far it's going to go horizontally in that time. And the key thing to recognize here is that, yes, we're separating the object's motion into its components, but really the object is moving through both axes at the same time. It's not like the boat actually split into two separate boats and somehow took a different amount of time to go downstream than to get across in that example we were just looking at, right? So the time is the same for all sides of both VAD triangles being velocity and displacement. Okay, so all the same steps apply. Okay, we're going to draw our diagram for each variable now because we're going to have to think about velocity and displacement for most of these. Okay, and then depending on the problem, there's kind of two ways you can go, right? Sometimes one is easier, sometimes it's just a matter of preference. But you can either solve for the angle with one and use it with the other diagram. Sometimes that's not always an option, so you have to go with option two. Option two being you can solve for time with one side of the triangle and then use it to find information about another side. But this is what we were talking about. We have to make sure the sides that we use to find time match. So we can find time with a y velocity and a y displacement using v equals d over t. But we could not mix our y velocity with our x displacement, right? Again, how fast that boat was going across the river has nothing to do with how far it ends up going downstream. How far it goes downstream just depends on how fast the water was carrying it downstream, right? Okay, so your vector addition diagrams are going to be super, super helpful as they have been throughout this lesson. But let's try one out. So a boat is 100 meters south of the shore. The boat has a still water speed of 15 meters per second, and the river flows at 6 meters per second to the east. How far off course will the boat be? So we got to read, carefully looking for clues, but it sounds like this boat tried to aim itself straight across, and as a result, the river carried it downstream, off course. Let's draw our diagram. So the boat is 100 meters south of the shore, so that means we have a displacement there, right? And it is a y-axis displacement. That is how far the boat needs to go vertically to get to shore, okay? Now, the boat has a still water speed of 15 meters per second, and from context, we can tell that the boat tried to aim that entirely in the y-axis, right? It just aimed its velocity straight north, okay? So that's a velocity in the y-axis. How far off course will the boat be if the river flows 6 meters per second to the east? So our river is flowing to the east, okay? So we can tell that our boat is going to end up off course from where it started. What we want to figure out is how far off course, right? We want to find the x displacement. So let's draw our VADs here. And remember, we're thinking about two different vectors. We're thinking about displacements and velocities. So we're going to need to draw two different VADs, one for each. So for displacement, what happened? Well, it did go 100 meters. It got to shore, right? But while it was doing that, it also displaced itself to the east because of the river's velocity there. So it did go 100 meters north, but at the same time it moved east, so that overall what it really did, it started here, it ended up here. Its actual displacement looks like that, okay? Now, switch our brains here to think about the velocities involved. Well, the boat had a velocity of 15 meters per second to the north, and while it had that velocity, it was having the water's velocity added to it, which was 6 meters per second to the east. So that overall, its real velocity was somewhere at an angle between north and east, right? So be very careful to make sure you don't mix up D's with V's. And we have to also be very careful, as we're about to see, to not mix our X's, our Y's, and our things at an angle. Okay, so for this one, it asked us to solve by using the angle. Okay, well, here's the thing, right? This displacement is how it actually moved, where it actually started to where it actually ended up. This is how fast it was moving in that direction, right? So that actually means that whatever this angle here is, it has to be the same angle as this, right? The resultant velocity was in this direction. The resultant displacement would be in that same direction, right? If you move in some direction, you get displaced in that direction. So those angles are the same. So take a look at our situation here then, right? If we knew if we knew the angle here, right? Well, we'd have the angle and adjacent. We could use tan to find the opposite, okay? Problem is, we don't have enough information in this triangle to find that angle. But if we look at our velocity VAD, we do have opposite and we do have adjacent. So we have enough information here to find the angle theta. And we know that's the same angle here. And once we have that angle, we can use it with tan to find our x displacement. So there's our game plan. We're going to use our velocity vector addition diagram to find the angle. And then once we have that angle, it's the same one here. So we can find it with the distance downstream, their x displacement with trigonometry. All right, so first things first, let's figure out this angle. Well, we have opposite, we have adjacent, TOA, we can use tan. So that means we can get theta with the inverse tan of 6 over 15. And that gave me that theta was 21.90 degrees. Okay, and now that we know this is 21.9 degrees, this also has to be 21.9 degrees. So let's head into step 2 here now, coming back to our displacement VAD. Well, we want opposite, we have adjacent. So once again, it's actually going to be tan that helps us out. But now we know that that angle is 21.9 degrees. So 21.9 degrees, or tan of 21.9 degrees, has to equal opposite, dx, that's what we're trying to find, over adjacent, 100 meters. Now, the only thing we don't know here is dx, so it's a solvable equation, right? Tan of 21.9 degrees, that's just a number. You can put it in your calculator. So dx is being divided by 100 meters. If we multiply both sides by 100 meters, we can solve for it. So doing that, I got that dx is 40.1997 meters, okay? Or two significant digits, that would be 40 meters. And which way? Well, to the east, right? So what we've worked out there is that the boat will end up 40 meters east of where they were, trying to go on the beach, okay? So 40 meters east of it. And again, all it required was thinking about how fast they're moving in each axis, right? How that relates to the angle, and then how that angle compares to the angle for the displacements. Okay, let's now try solving it again by using time. Sometimes we actually can't do this. You'll see what happens when we do a compensation problem this way. The angle stuff doesn't work out, but we can always use time. So let's solve this one again by now thinking about time. I'm just going to copy and paste all our diagram stuff because nothing's changed here for our diagrams. Okay, so remember this, right? The rate at which the vertical displacement changes is the vertical velocity, right? The rate at which the horizontal distance changes is the horizontal velocity, okay? And this dr, the rate at which this changes, is this vr, okay? So we can't mix those. It doesn't make sense to say that it traveled 100 meters going 6 meters per second, right? Because that 6 meters per second had nothing to do with taking it across the river. How fast it got across the river is going to come down to the fact that, well, it was aimed across the river at 15 meters per second, and it had to go 100 meters to get across, right? What we're looking for here is sides of our triangles that match, so to speak, right? So the boat really did vertically travel 100 meters, and its vertical velocity really was 15 meters each second, okay? Right? We don't know how far it went horizontally yet, but we know it was going that fast at it was moving through that displacement at a velocity of 6 meters per second. So if we knew how long it was moving horizontally at 6 meters per second, well, we could figure out how far it would go, right? We know that horizontally it goes 6 meters each second. We just don't know how many seconds it was doing that for. If we did, we could say how far it would go, right? What we do know, though, is that vertically it went 100 meters, and while traveling at 15 meters each second. So with those two pieces of information, well, we can figure out how long would it take for something going 15 meters each second to travel 100 meters. And then once we have that time, we know that the boat was moving horizontally at 6 meters per second for that amount of time, right? We separated into the components, but it was doing both things at the same time. It was going across the river. At the same time, it was being carried downstream. Okay, so there's our plan there. We can use these matching vectors here, the vertical displacement and the vertical velocity, to figure out how much time would pass. Those match. Okay, so we can use this equation, right? The rate at which the y displacement changes is the y velocity. Okay, so let's write out our equation here. Our y velocity is the velocity the boat is aiming with, and our y displacement we know is 100. I'm just going to put it in symbolically for now. Okay, we want to solve for time. Right now it's in the denominator. So first things first, let's just get it out of the denominator by multiplying both sides by time, and that leaves us with time times the boat's velocity will equal its vertical displacement, right? Again, that makes sense. If it was moving 15 meters per second in the y-axis, well, multiply it by how many seconds it's been to figure out how far it would go, okay? Now, t times v equals d. We want to solve for t, so let's divide both sides by v. And we get that the time this would take is equal to the displacement it traveled by the velocity with which it was traveling in that axis. So it did travel 100 meters vertically, and it was moving at 15 meters per second vertically, right? It went 100 meters north while going 15 meters per second to the north. And so doing that, I got that the time that would have passed in order for it to go 100 meters if it was moving at 15 meters per second in that direction was 6.666 repeating seconds. Okay, so think about what we've got here now. We now know how long the boat took to cross the river, right? And we also know how fast it was moving to the east while it was crossing. So if I said to you, even back in Science 10, hey, something was going 6 meters per second and it did it for 6.67 seconds, how far did it go? Would you be able to answer that question? Yeah, you would, right? You know how far it was going each second, and you know the number of seconds it must have been doing that, right? So we were able to get the time it would take to cross, and now we know that that whole time it was moving 6 meters per second to the east. We can find how far it would have gone. We can find dx, the horizontal displacement it traveled during that time. And again, just making sure we're, doing horizontal velocities with horizontal displacements. So the x velocity is the rate at which the x displacement changes. Has nothing to do with the y, right? But it does have to do with the horizontal, the x. Okay, so if our water, right, the rate at which our displacement changes just depends on the water's speed. Okay, we can solve by multiplying both sides by t. And we get this statement here that makes a lot of sense, right? How far it ends up downstream just depends on the velocity of the water. Makes sense because the velocity of the water is the only thing carrying it downstream, right? Times how long the velocity was carrying it downstream. So putting in our numbers, we know that the velocity of the water is 6 meters per second. And now, thanks to our y-axis, we know that the amount of time it was doing that for was 6.6667 seconds. Okay, so multiplying those two together, I got, 40 meters, right? And again, to the east. So notice, that's the exact same as we got by using the angle. Both are perfectly valid approaches. Okay, so you can, depending on the problem, you sometimes can't use the angle. You'll know it when you see it, like we'll see in this next example. Okay, you can always use the time though, right? As long as you are very careful. That's the number one student mistake that comes with this, is mixing up a y with a, something at an angle, or an x with a y, or an x with something that's at an angle. You have to be sure that you're using matching sides of the triangle, right? A vertical displacement can be used with a vertical velocity, right? But a vertical displacement can't be used with a horizontal velocity. Okay, last example, and then we're all done with the notes, and you're ready for more practice. So here we have that a ferry must reach a dock directly north across a 100-meter wide river. Okay, let's just start our diagram right away. So the ferry needs to go directly north to the dock across a 100-meter wide river. So that is the vertical displacement, right, to the north. So it does need to go 100 meters in the y-axis. The ferry has a still water speed of 4 meters per second. Okay, I'm not going to draw that in yet because I first need to figure out if it's a compensation or off course, right? I don't know which way it's aiming. And the river flows at 1.5 meters per second west. Okay, so the velocity of our water is to the west. There we go. If the ferry successfully compensates for the current, we want to calculate its heading and the time it will take. Okay, so successfully compensates. How does this this boat need to aim its velocity to compensate for this? Pause the video, take a second, think about that. Well, since the water's flowing to the west, if it wants to go straight across, right, it needs to have no x component overall to its resultant velocity, right? So that means this x component that's going to be part of its velocity needs to get canceled out by something else. So the boat's going to need to aim something like that so that its x component cancels out with the water, which is in the x-axis as well, making its resultant velocity be actually straight across. So let's go ahead and draw our vector addition diagrams, okay? Let's first do it for displacement. Okay, now this is going to look a little bit different than this example because now there should be, well, I'll ask you, what should be the x displacement, the horizontal displacement, if they successfully compensate, meaning they get to the dock, right? There actually is no x displacement, right? If they displace themselves in the x-axis, that means they went off course. They didn't make it to the dock. So they are going to go straight across the river, and that's actually it, right? They're going to successfully compensate so that from where they start to where they end up in terms of position is just straight across. So dy is actually dr, right? The resultant displacement should just be the 100 meters north to get across the river. Now in our velocity vector addition diagram, how they achieved that so that their resultant displacement was straight across the river, well, we already talked about that, right? They aimed to the east just enough that that canceled out with the water's velocity, and therefore their resultant velocity is straight across the river, right? So here's what I was referring to when I said the angles aren't always an option to us, right? Because in this case, our displacement, it's not actually part of a triangle, right? Our resultant displacement really was just straight across the river. In order to achieve that, we had to do our velocity at some angle to cancel out with that, right? Now you can see our VR and our DR are still in the same direction, right? But that direction is just north, which we already kind of knew. So we can't use an angle here, okay? But what we can do is recognize that the velocity that it had across the river, right, and the resultant displacement, which was across the river, those kind of match, right? However fast it ended up moving across the river is going to determine how long it took to go across the river. It has 100 meters to go. If we can figure out how fast it was actually moving in that direction, we can figure out the time it would take, right? So looking here again, okay, ultimately it has to travel a vertical distance, okay? And the velocity that it's going in the vertical direction is what determines how long it's going to take, okay? So you'll notice here when I run it, remember before it took it about 10 seconds to cross? Well, now it's taking like 13 seconds, which actually makes sense because it's giving some of its velocity. It's kind of sacrificing some across the river velocity in order to cancel out the sideways velocity, right? So it does take a little bit longer to get across because now all of its velocity isn't aimed across. Some of it is used to fight the river current. So we know how far it went resultant, right? It went 100 meters north, okay? If we could figure out how fast it went north, we could figure out how long it would take to go 100 meters, right? So let's go ahead. We've got these matching here. I can use a v equals d over t. It looks like I'm doing b first. Whoops, I kind of skipped A. We'll do A in a sec here, okay? But if I have a matching V and a matching D, I can figure out the time, right? Now, I could not use the boat's velocity here because the boat's velocity is not how fast it was moving across the river. It's how fast it was aimed in this direction, right? So that's what I mean. We always need to make sure our vectors match if we're going to use them to find time. So here we go. We know that the resultant velocity will be equal to the rate at which the resultant displacement changed, right? How much it changed per second, okay? We do know the resultant displacement, it's 100 meters. We want to know the time. We don't have the resultant velocity. But hang on a sec, we do have the velocity of the water, it's 1.5 meters per second, and we do have the velocity of the boat, it's 4 meters per second. So look at this. We've got two sides of a right angle triangle. We can find the third. So there's our plan. Let's find the resultant velocity. And then with that resultant velocity and the resultant displacement, we can figure out how long it must have been traveling for. Okay, so this is just Pythagorean theorem, but be very careful. Super common student mistake is to just assume VR is the hypotenuse of the triangle, right? But it's not in this case, right? VR, like we talked about, is actually a little bit slower than the velocity of the boat because, again, it's sacrificing some of its velocity in order to fight this current, right? Some of its velocity is going into just overcoming that current. And so as a result, it doesn't move across as fast as it could if it just went straight. Of course, then it would end up off course. So, long story short, that is not the hypotenuse. Be careful. C squared equals A squared plus B squared. C squared must be the hypotenuse. So the velocity of our boat squared is going to equal the resultant velocity squared plus the velocity of the water squared. Okay, so we're not solving for this. We already know that. We're actually solving for this. So bed mass, reverse bed mass, we need to isolate VR. It's being squared and it's having this added. First, we need to deal with the addition. So let's subtract V water squared from both sides. Okay, and then VR squared, we want to square root both sides to undo that. And there we have it. The resultant velocity is going to equal the square root of the boat's velocity squared minus the water's velocity squared. Okay, let's go ahead and put in our numbers. And then calculating it out, I got that it would be at 3.7081 meters per second. Okay, so again, right, now we're back in, Science 10. I'm saying that it went this far, it went 100 meters, and it was traveling in that direction at 3.7 meters per second. We can figure out how long it must have been traveling then with just d over t, right? We already knew the resultant displacement, and now we also know the resultant velocity. So we can solve for the one unknown, time. So we can see we're good. These match, right? We're talking about the same things there. VR is the rate at which dr changes. Let's multiply both sides by time, and then divide both sides by VR to solve for time. And we're ready to plug in our numbers. So it did go 100 meters to the north, and it was traveling at 3.7081 meters per second to the north. That's its resultant velocity. Okay, so dividing 100 by that speed, I got that it should have taken 26.9679 seconds, right? It was moving across the river at that velocity, and it did have to go 100 meters to get there. So that must have taken to two significant digits, 27 seconds. Okay, so that was part B. We actually did part B first, okay? That was really the new part. Part A we've done already in this lesson, so I wanted to focus more on that, okay? But again, same principles as before. We need to draw out our vector addition diagrams, okay? And then the other variable we are going to have to think about here to connect our two diagrams is the time, right? And we need to be very careful that we're choosing matching vectors. We can use VR with dr to find time, but we can't use vboat with resultant displacement to find the time, right? Those aren't matching vectors. It wasn't moving at 4 meters per second straight across. So we can't use the displacement straight across with that velocity. It just wouldn't make sense. All right, we can quickly do part A here as well. In fact, it's just going to boil down to using our VAD again. We're being asked the heading, so which way should it aim, which direction? Well, this is the direction it aimed, okay? We could describe that with an angle, and we have opposite and hypotenuse. So opposite, hypotenuse, that makes me think of sine. And therefore, theta will be the inverse sine of opposite over hypotenuse, 1.5 over 4, giving me that theta is 22 degrees. And in this case, looks like it would be east of north. East of north. All right. Okay, so sometimes students will say to me, like, how do I know if it's one where I can use the angle or one where I can't use the angle? And my response to them is usually, well, did you draw your diagrams? Because once you draw your diagrams, you see pretty quickly whether or not you're going to be able to use an angle to solve it. Right? It's no special rule or anything. It's just that, oh yeah, because they compensated, their resultant displacement is actually just straight across, right? There's only one displacement to think about. It's the y-axis displacement, right? Now, in order to achieve that, the velocities had to be directed at an angle to compensate for the x-axis stuff and all that, right? But we can't make use of an angle here because there's just different stuff going on, right? Compared to here, where it really did end up going at this velocity and therefore traveling through that displacement, right? So we can see once you draw your diagrams, which is kind of the story for this whole lesson, drawing the diagrams makes things a million times clearer. In fact, it's like most of the solution is drawing your correct diagram. From there, it's just the Pythagorean theorem usually, or some SOHCAHTOA. Okay, so that wraps up the notes and examples for this lesson. You are now all good to complete the rest of the practice problems, okay, that are assigned. A good place to start, though, actually, remember earlier that one you did? You can now do part B of that one, which just brings in another layer where you're going to use the time, or use the both vectors to figure out the time it takes to cross, okay? So once you're done that, you can work on the rest of the remaining practice problems there, okay? And as always, make sure you're reaching out for help as needed. Important to get that practice, but also important to recognize when you might need to talk through some stuff with me a bit too. Okay, so send me an email, book a meeting. I'm always happy to help. But there we go, we're done.